Check it out now, y'all.
nanoHUB-U, online instruction.
This is the solution to homework 1, and homework 1 is based on material covered in week 1, which really dealt with equivalent point mass oscillator models for cantilever probes. And really the point was made that it's these correct point mass oscillator models that allow us to, in future weeks, really go into some detail to understand the links between the observables in dynamic AFM methods and the local properties. All right. So just to quick summarize how the solution is laid out, the correct answers to every problem are highlighted in yellow, and the answer and the solution strategy to each one is just given right following each problem. All right, so let's quickly go through some of the key solutions here and see what insights we might get. The first problem is about equivalent stiffness and mass, and you have two oscillators, two probes with the same stiffness, or different stiffness, but the same natural frequency, 40 kilohertz, and they're set to oscillate at an amplitude of 1 nanometers without forcing or damping. And so what happens here is, you're basically given this, and you're given that the natural frequency are the same, which means that, the only way you're going to have the stiffness of 2 being 10 times greater than the stiffness of 1, and yet have the same natural frequency is if the mass of the second is also 10 times larger than the mass of the first. However, we're also given that both oscillators are set to oscillate with the same amplitude, and they have the same frequency. So the amplitude and frequency of oscillation are the same. Both probes must be oscillating with the same velocity. And keep in mind that the kinetic energy is basically going to be 1/2 the equivalent mass of the probe times the velocity squared. If the velocity is the same in the two probes, then the kinetic energy must scale by the mass, and therefore the kinetic energy of the second probe is going to be larger, even though the two probes have the same resonance frequency. Okay? Let's go to problem 2. Problem 2 is about settling times. So what's really interesting about this problem is the idea is to sort of do away with a preconception that is often there, which is, folks say that if the Q factor of a cantilever is small, that means that settling time is smaller. So here we got an example. We got a probe with a Q factor of 60, but with a low frequency, 50 kilohertz, and then you got another cantilever with a Q factor of 300, but with a faster or more rapid natural frequency. So on the face of it, you might think that cantilever A, having a lower Q factor, would actually settle faster. Turns out it's not the case. And the key result here has to do with the fact that when we looked at how much time it takes for the vibrations to decay to, let's say, 13% of the original value, that time, the decay time or the settling time, scales as the Q factor divided by the natural frequency. So probe 1 has a lower Q factor, however it has an even lower resonance frequency. All right, so when you compare the Q over omegas, or Q over natural frequencies of the two cantilevers, for cantilever 1 you have a Q factor of 60 divided by 50 kilohertz. For cantilever 2, you have a Q factor of 300 divided by a natural frequency of 300, right? So you can see that this number is larger than that number, therefore settling time for the first probe is actually longer than for the second probe. Or in other words, the second probe needs less settling time. But the natural frequency of the second probe is much higher, so the same settling time, it's going to oscillate many more cycles. So the correct answer is C here. Okay. Problem 3 deals with magnetically excited cantilever probes, and the idea here is if you were to plot as I had, I guess, shown in class, the amplitude as a function of drive frequency, magnetically excited cantilevers behave like this. And we're basically comparing the amplitude at resonance to amplitude at zero excitation frequency, and trying to see what kind of amplification is achieved. In other words, the fact that you actually reach a larger amplitude while exciting the cantilever at resonance than you do far below resonance. In any case, to get to this problem, you just go to the transfer function that we derived in class and set R, which is the ratio of the drive frequency to the natural frequency, to be equal to 0, and then you set it equal to 1 in this expression, and you actually find that the ratio of this amplitude at resonance to that amplitude far below resonance is actually Q. So it's a very interesting way to interpret what the Q factor means. Is, when you're oscillating magnetically or directly exciting the cantilever far below resonance to at resonance, that ratio is basically Q. All right. So the answer is going to be B in this case. Let's go to problem 4. Problem 4 is perhaps probably the most complicated of problems in this particular homework. And it asks you to compare the measured amplitude when driving above resonance to below resonance, but also to compare the absolute tip amplitude above resonance to below resonance. And you will remember that these two situations are slightly different for acoustic and or base excitation and directly excited methods, right? And we had derived and compare this. What we have to do is to keep in mind that if this is the base of the probe and if that is the probe tip, then as the base of the probe moves up Z base, what ends up happening is that there's an absolute tip motion up Q, right? But relative to the base, there is a motion Q rel, right? And that's what is really measured by the AFM photodetector, is a bending of the cantilever, or the tip motion relative to the base, and the absolute tip motion is not really picked up by the photodetector. So what we need to do is in order to answer this question, we need to derive an expression for the transfer function of the base excited cantilever, but in terms of the absolute Q relative to the base motion Z. And to do that, we just go back to the equation we had derived at the start in the class before converting it into all the quantities referred to the base, and we reach this equation. And this equation, which we derived in class, is basically the same form as the directly magnetically excited cantilever, right? In the case of the magnetically excited cantilever, you had the magnitude of the force on the right hand side, but otherwise it was basically the same equation. Q is now the absolute motion of the tip, and so if you simply write down Q as some absolute vibration amplitude times sine omega t minus phi, right? You can actually solve for the transfer function between A absolute and this Z naught, which is the magnitude of base motion. In fact, this transfer function is identical to the directly excited cantilever transfer function, and is shown here. Right, and which tells us that if one is going to plot A absolute as a function of omega, right, one would get a curve that looks something like this. Okay, exactly like in the magnetic case. However, we had derived an expression for what is the transfer function when you try to relate the relative, relative tip motion relative to base motion, relative to the magnitude of the base motion, and you get a much more complicated transfer function. And if you recall, the shape of that magnitude of the transfer function takes the following form, and I might try to display it on the same axis by plotting a rel here. That takes a very different form, and that actually does this. Something like this, as we discussed in class. So what ends up happening is that when you're below resonance, the absolute tip motion is more than the measured tip motion, but when you're above resonance, the absolute tip motion is much less than the base motion. In fact, when you go far above resonance, you have this very peculiar situation where the tip motion, the motion of the tip itself, absolute motion, is not much, it's hardly moving, but the base of the cantilever is moving up and down, whereas the absolute tip, the tip has no absolute motion at all. So these kind of interesting things can actually happen when you do acoustic excitation. You can also get to the answer by simply plugging in numbers into these two transfer functions and seeing which reaches a larger magnitude before or after resonance. So the answer turns out to be A here, and with that we can move on to the next problem. The next problem is that of thermal calibration of stiffness. You're given the thermal spectrum of 3 different cantilevers here. It helps to break this problem out into 2 parts. First compare cantilever 1 and 2, and then we'll compare cantilever 2 and 3. So if you compare cantilever 1 and 2, the red and green, you find interestingly that the area under the curve, the power spectral density of the 2 cantilevers, is pretty similar. How do I reach that conclusion? Well, if you look at this region, where the red has more area, and this region where the red has more area compared to the green. But if we compare it with this region where the green has more area compared to the red, they roughly cancel out. So which suggests that the area under the curves is roughly the same. And remember, we have this relationship that 1/2 K equivalent times the area under the curve, which is basically the mean squared tip deflection, must be equal to 1/2 kBt, where kB is the Boltzmann constant, T is the temperature, which means that if this quantity is identical for 2 cantilevers, well, this right-hand side has to be identical for every cantilever because it's a universal constant. So if this quantity, which is the area under the power spectral density, is the same for the 2, this must mean that K must be same for the 2, which tells us that K1 must be equal to K2. But clearly, cantilever 2 has a sharper peak. So we must have Q2 greater than Q1. Right? In a similar manner, if we compare cantilevers 2 and 3, we find that the area under the power spectrum of 2 is going to be much more than the area under the power spectrum of cantilever 3. Which means that the spring constant of cantilever 3 is much smaller than that of 2. However, if you look at the shape or how sharp this is compared to the green curve, they're very similar. They're equally sharp, except one is scaled up compared to the other. So this tells us that Q3 in fact must be equal to Q2. So putting these two results together, we actually get to the right answer, which happens to be B. All right. Finally, we get to problem 6, which is dealing with the conservative tip-sample interaction force, which is always repulsive in that the value of the interaction force is always greater than 0. But we want to understand how the natural frequency of the oscillator omega naught prime would change as you come close in the limit of infinitesimal tip vibrations. Now, the intent of this problem is to kind of emphasize the fact that, it's not the fact that the interaction force is repulsive or attractive. Really what matters the most is the gradient of these interaction forces, right? So, if this is the FTS, if I were to, on the same axis, plot what the KTS would look like, right, which is negative partial F partial D, the KTS would look as follows, right? I'd have a repulsive gradient, a positive gradient, but at the point where this reaches 0, the gradient would become 0, and then here also the gradient would become 0, and then it would actually come out after that, right? Which suggests that if you go back to the formula we derived in the class, which connected the modified natural frequency to the gradient observed, it's very clear that the resonance frequency, natural frequency, should change according to this green curve, or proportional to this green curve, which tells us that the frequency shift therefore must be initially positive and then go a little negative here, as shown here, and then become positive again. So the answer must be D. All right.